Okay, let's look at orthofloat.c. This is a by one orthohack transform. This is what you would actually deploy in a product. You could also analogously think of orthofix.c or orthocustom.c if you're into fixed point transforms instead. So first of all, we have these Unixy-like includes. This just is kind of to pacify C and some of the types it uses. There's no operating system calls or anything like that necessary. We always need orthoconstant.h and of course the generated orthohack file. And orthodim to give us the dimensionality of numbers. And of course, at the moment, there's only real numbers supported, so dimensionality 1. Orthonumber, this abstracts all of the arithmetic operations for floating point that we'll be using here. Orthotable, this contains a lightly compressed representation of the instructions required to build the binary tree and also to execute the transform. And we'll go into exactly how the transform works below. Orthofloat table, this is basically just the number underscore list from Orthohack embedded in memory. So to initialize things, all we actually do is we set the first index of the monomial list to 0. This is just done because theoretically it's possible that after the post processor, a bunch of numbers actually evaluate to 0. A bunch of different binomials will evaluate to 0, in which case potentially you could point them all to the first index and get some cache efficiency out of that. At least that was the thinking. It turns out that this is probably not necessary to do, but if you want to undo it, you have to change all the +1 indices and so forth, and it's probably not worth the trouble at this point. Okay, so more importantly, the orthofloat transform, we're taking in a monomial list, and again, what is defined in this list? Only the first element, which is 0, and the next sample underscore index underscore max elements, which are the sample indices. And remember, sample index max in this case is 64 because we need to account for the first item being 0. So you have all 64 samples copied into the monomial list. And the coefficient list is undefined apart from its size, which is coef count numbers there. So the first thing we do is, in fact, we zero the entire coefficient list because we're going to be adding stuff to it below. And then we need to create all the binomials. So, and there are a binomial count of them. And so in this orthobinomial by one, all this is doing is it's unpacking the list of instructions for assembling the binomials. And basically how you do that is one of the things that pops out is this ratio index. And the ratio index essentially is an index into the number list of the ratio we're going to multiply by, but it also contains sign information. And in real numbers, there's only one sign bit. So we actually go down, and after we fetch the ratio out of the list, we multiply by the sign, and the sign is 1 for negative, 0 for positive. But if we were to add complex or quaternions later, for complex, we'd have 2 sign bits, one for real, one for imaginary, and for quaternions, we'd have 4, etc. So we do this shift here in order to obtain the actual index into the list from whence we fetch the ratio, which is a floating point. And by the way, notice this cast to number star here. This is because number list base is actually bytes, and we're casting to a number. It's kind of ugly, but I'm sure you can deal with that somehow. And then finally, we compute the value of the binomial. I just call this monomial because later we treat the initial samples and the binomials all as being quote-unquote monomials. And so you should recognize this operation here. This is just essentially operation A from ortholiteral header.c. We're just taking a numerator value, which was fetched when we unpacked it, and we're multiplying it by the ratio that we just fetched. And then finally, we're adding it to a denominator, and the denominator is also computed in here. And we're doing that for binomial count. So now, as of here, all of the binomials have been computed. Now we're going to go through and actually follow the transform instructions. So basically, the transform works like this. Some of the sample points and some of the binomials are actually used. And by used, I mean that they're multiplied by various constants and added to various coefficients. Others are purely used for the purposes of generating other binomials, and so actually they're no longer necessary at this point. So what we do is we skip big blocks of binomials that we don't need to use, and then later we actually process those binomials that we do need to use. So the first thing here is all that's in here is basically instructions that find out how many monomials in a row are 0, and we skip them, and we don't do anything. But then we find the non-zero monomials. Those are the ones that we care about. And basically, there are some n of these, and the n is monomial count specifically. Monomial count was set in this include file. And basically, for monomial count monomials, we have to do the following. So the first thing is we want to figure out what is the alias count. So an alias is just simply an alias for a monomial, which consists of an index into the ratio table and a coefficient to which to add the product of the ratio and the monomial that's sitting in memory. So for each non-zero monomial, we might have, a certain number of aliases, and they can vary per monomial. So one monomial might only be multiplied and added to, one coefficient, and one other one might be added to 10,000 coefficients. So then this next loop is a loop over the number of aliases, and we basically unpack one at a time these ratio index coefficient index pairs. So you can see we're extracting the ratio indices exactly as before and setting the sign. And we're also taking whichever monomial that we need to multiply by. We're popping that out into monomial. And ultimately, we set the monomial to the product of itself and the ratio that we just fetched. And we add it to the target coefficient. So this is, we're loading the coefficient, adding the monomial, the scaled monomial, and we're storing back the coefficient. And that's how it works.